So just before we get started, let me remind you, because it's a lot of details to what I'm talking about. What we're trying to figure out is what is voltage, what is current, what is resistance. Now, what you're going to learn is that there's a constant relationship between voltage and current. Voltage is the cause of a current. So we want to answer the question first, what is voltage? And once we understand what voltage is, you'll understand how we can take a voltage and make a current. So that's the idea here. So in understanding what voltage is, how do I make voltage? What is voltage? I put these three terms on the board, and we went through on Friday and we defined these. And I don't know what I said exactly, but more or less this is the definitions we came up with. Energy is the ability to do work. Energy is the ability to do work, and we said that the unit for energy is the joule, and they use a capital J for that, for joule, and that's the unit for energy. And we said, all right, well, if energy is the ability to do work, what's work? And we said work is what happens when a force acts on an object and makes it move through a distance. Work is what happens when a force acts on an object and makes that object move through a distance. So that's two things you got to think about. If I want work to happen, number one, I got to have a force. You can't have no work with no force. And number two, the force has to make something move. If there's no motion, there's no work. If there's no force, there's no work. And we also mentioned the fact that work also has joules as a unit, which is interesting. So we have energy and work having the same joules. So then I stated the conservation of energy principle. Energy cannot be created or destroyed. You can only change it from one type to another. Well, what do you mean by that? Well, in the whole universe, there's only two types of energy. No matter what you tell me, what kind of energy you name, I could put it under one category or the other. There's potential energy and there's kinetic energy, and we talked about that. And so what we're saying is that potential energy can become kinetic. Kinetic can become potential. You can make one go to the other, but those joules just can't disappear. So I kind of rephrased that. I said instead of saying energy is conserved, let's say joules are conserved. All joules are conserved, and the reason I said that is not only is energy measured in joules, but work I do to get energy is also measured in joules. So we're going to say all joules are conserved. And in essence, what I'm saying, if you do work, if you have work, you perform work, then those joules of work that you perform have to go somewhere. They're either going to go into potential energy or kinetic energy. So it's this play between the three that we'll review here in just a second. And so we said force acting on the object and making an object move through a distance means work is happening. And then I said, all right, what's force? And we said, well, force is a push or pull. Force is a push or pull. And that's when we got to this idea of two types of forces. And I do remember now, we talked about force. And one type of force is called a contact force. And the other type of force has a long name. It's called an action at a distance force. An action at a distance force. And so we talked about contact forces. That's when I have two objects. That's when I have two objects, maybe my finger and the eraser, and they actually touch each other. So there's two forces, right? Newton says that you got to have two forces. There's the force of my finger on the marker, and there's the force of a marker on my finger. If I push it hard enough, I can make the eraser move, and that means I'm doing work on the eraser. And so we talked about that, a contact force. My finger is in contact with the eraser is in contact with my finger, and I can transfer forces through contact. But then there's a whole nother class of forces. These are special forces called action at a distance forces. An action at a distance force would be a situation where I have an object and I have another object. Object A can exert a force on object B, but they never touch each other. And I think we ran out of time and I asked for an example of that. And I believe, if I'm not mistaken, because I've done this lecture like 3 times, so I don't know who I told what. If I'm not mistaken, somebody correctly said magnetism. You've all played with magnets, and magnets behave exactly like I just described. If I have two strong magnets on a smooth surface, imagine I have two really strong magnets on a piece of glass. If I slowly bring, and I have a north pole and a north pole, like poles repel each other. So if I slowly bring the first magnet over to the second, then eventually when I get close enough, that second magnet moves away and they never have to touch each other. Here's a case where I have a force acting through a distance, the two objects never have to touch each other. Can anybody tell me a second example of an action at a distance force? Give me another example of an action at a distance force.
Would wind be one?
Okay, weight. Well, I know what you're saying. So you said, would weight be one? So like, what is weight? So if I have an object, and that object has mass, and that means that it's attracted to other objects that have mass. So if I have this bottle of water and this case or whatever this thing is I got in my hand, there's actually a force of attraction between these two. You might say to yourself, well, that's kind of, how come we don't see masses sticking against each other? Because the force of attraction between masses is really, 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 really weak unless the masses are real big. And so if I hold this object up, I feel the weight of it, but what you mean by weight is I feel the earth pulling down on this. And remember, Newton says there's got to be two forces. You can't have just one. There's a force of the earth pulling down on the object. I call that weight. There's a force of the object pulling up on the earth. Well, the earth is so much bigger than this. I never see the earth come up and meet the object. If I drop this, I always see the object go down and meet the earth. But some kind of way, the earth is pulling down on this object, but yet this object and the earth are never touching each other. What do we call that? We call that the force of what? You fill in the blank.
Gravity.
The force of
gravity.
Gravity. So gravity, just like magnetism, is another action at a distance force. When they send a rocket to space, to go to the space station or to launch a satellite, the rocket is sitting there on the pad full of fuel, and the engine turns over, the engine fires, and the thing slowly lifts up, and eventually it starts to burn off fuel. It gets lighter and gets further away from the earth. The gravitational pull of the earth on the rocket lessens as the rocket gets further and further and further. Gravity is another action at a distance force. Gravity. And there's one more. There's one more in nature that we know about, one more action at a distance force. Can anybody tell me what it is? We've already talked about it. Think about it.
Static.
Say again?
Static.
Okay. Well, static or charge. Remember, the law of charge, if I have like charges, if I have a plus charge here and a plus charge here, like charges repel. So if I have these two charges, if I bring one positive charge over close to another, it will eventually push the other one away. They never have to touch each other. If I have two negative charges, the same thing happens. If I have a positive and negative charge, I still get a force, but instead of a force of repulsion, now it's a force of attraction, but still it is a action at a distance force. Those two charges never have to touch each other, but one to exert a force on the other. So the third and final action at a distance force is called the electric force, or another name is a Coulomb force. Let me put that on the board. The Coulomb force. A Coulomb force is just another name for electric force. These are the same. So this is some cool stuff. I actually have one object that can exert a force on another object through free space, and they never have to touch each other. Now let me ask a question. Now think about this. What one thing do these three forces have in common? There's one thing that magnetism, gravity, and the electric force, they all have a blank. They all have a what?
A charge.
Not charge.
Energy.
Energy.
Here's the F. They all have a what?
Force.
You see a force?
Yeah.
I'll give you the next letter. I.
Friction.
I think I'm spelling it. No. You play sports on it.
A field.
Yes. They all have a field. You heard of the magnetic field. Maybe when you were in high school or junior high school, you ever take a magnet. Sometimes they'll take a magnet, put it on a piece of paper like this, and they'll take iron shavings or filings, put it in like a pepper shaker, little tiny piece of metal, and they'll sprinkle it on there like salt and move it around. You can actually see the orientation of the magnetic field. There's a magnetic field that exists between two magnets. And then what about gravity? Well, you know, we just gave the example of the rocket ship trying to escape Earth's gravitational field. And then the electric field. There's actually a field between two charges. So this idea of a field, there's the electric field, there's the magnetic field, and there's a gravitational field. So some kind of way, only unique to action and distance forces is this concept of a field. Now, what is a field? Don't answer it because we don't know the answer to that. We don't know what a field is. In science, sometimes we don't know what things are, but we still got to work with them. So here's what we do. When we give a definition of something, scientists like to define things in terms of what they are. And anytime they can do that, that's what they do. But sometimes we don't know what charge is. We don't know what gravity is. So if we don't know what something is, we define it in terms of what it does or how it acts. That's called an operational definition. It's unique to science. Instead of defining something as what it is, we define it in terms of how it operates or what it does. And so a field is the mechanism through which forces are transferred through free space or energy is transferred through free space. I'll say that a second time. A field, a gravitational field, a magnetic field, an electric field, doesn't matter what kind of field we're talking about. There's some kind of region between two objects, two masses. So it's the mechanism that connects these two regions, and through that invisible mechanism, we can transfer energy and we can transfer forces. And that's pretty cool. So if I have a gravitational field, I can hold up an object and gravity's pulling down on this. The Earth is actually reaching up, pulling down on this object through its field. It's invisible gravitational field. If I have two magnets and those magnets get close enough to each other, there's actually something connecting the two magnets. There's an invisible field, and through that field, force is transferred, so the other object can move away, or energy is transferred. I mean, think about it. If I have a magnet and I move it close enough to the other magnet and it moves away, that's the definition of work. That's the definition of joules being transferred from one place to another. So I can cause work to happen and the two objects never have to touch each other. And then the final example, the electric field, the same way. I can have two charges. Something's got to connect those two charges. It doesn't matter if it's air, if it's a vacuum, that field can travel from one charge to the other through free space, and it can transfer forces to that second charge. It can transfer energy to the second charge. Energy in the sense that if I move this charge close enough, it can do work on the second charge, apply force, and make it move through a distance, making those joules move. It can apply work. Now, this is exactly what we need to happen, because here's what we got to do to make electric current. If I want to make an electric current, what I got to do is take charge that ain't moving. I got to make it move. So how do you take something that's not moving? How do you take something that's not moving and move it? Well, obviously you push it. The problem is we can't push electrons. They're too small. So how do I apply a force on an electron that's not moving to make it move, to turn it into electric current? The way I do that is applying a force, not this kind of force, but this kind of force. And you'll see that in just a second. Now, let me go back to this work-energy relationship, because this is where we start to get into voltage. What is voltage? We're about to answer that question. So let me remind you about energy. We said there were two types of energy. There's potential energy, and there is kinetic energy. Potential energy is stored energy. Potential energy is stored energy. I can have energy stored in an object because of its position. That's gravitational potential energy. Or I can have energy stored in the object because of its condition, like the condition of a string being stretched or compressed, or a piece of metal being bent, not bent to where you deform the material, but bent to where it'll spring back in the original position. If I bend it a little bit, if I bend a stick a little bit, or a piece of metal, there's energy stored in there. There's potential energy. And when I release it, however much work, how many joules of work I use to bend the material is exactly the joules I get back. Now, in an ideal situation, there's always losses. We're talking about ideal situations. I can store energy through an object's position. I can store energy, object's condition. Kinetic energy is energy of motion. Kinetic energy is when you do work, something's got to move, which means that thing that's moving has kinetic energy. And kinetic energy is the only kind of energy that can do work. That's important. Kinetic energy is the only kind of energy that can do work. So if I want to do some work, there's got to be some kinetic energy happening somewhere. Some object, something, something's got to have kinetic energy, which means something's got to move. So let me go back to the example from last class. I have an object. I want to move it from point A to point B. So if I want to do that, I got to do work. I got to apply force, and that force has to act through a distance to make the object move from point A to point B. But all joules are conserved. The joules of work that I exert on the object moving it from point A to point B, they can't just disappear. They got to go somewhere. So if I do 10 joules of work moving the object from point A to point B, those 10 joules are now stored in the object as potential energy. Gravitational potential energy. I say there's a gravitational potential difference. Listen, there's a gravitational potential difference between this point and this point. I now have potential energy. The beauty of potential energy is I can turn it to kinetic energy. If I want to turn it to kinetic energy, all I got to do is let it go. If I did 10 joules of work moving it from point A to point B, I have 10 joules now stored in the object as potential energy. If I want to get that energy back, I let it go. As I let it go, it sticks there for just a nanosecond. It's sitting there, and then gravity takes over and starts to pull down on it. So now my gravitational potential energy is decreasing, but at the same rate that the potential energy is decreasing, the kinetic energy is increasing, because kinetic energy is related to the object's speed. At first, the speed is zero. It's all potential energy. And when gravity takes over and pulls down on it, now starts to speed up, the potential energy is decreasing, but the kinetic energy is increasing. And right before this object gets to point A, where it started from, I have exactly 10 joules of energy here, but now that energy can do work. When I have kinetic energy, it can do work. If this was a brick, and I have a stake, I can drop this and hammer the stake into the ground. I can make something happen with kinetic energy. Gravitational potential difference can cause work to happen through kinetic energy. Now here's the beauty of this whole discussion. Exactly what I told you about mass, the same logic applies to charge. Let me show you what I'm talking about. Say I have two charges. I got two charges, and you know, like charges repel, but those are unlike charges, so they attract you. They're stuck together right now. And what I want to do is I want to separate these two charges just like I separated the mass of my hand from the mass of the object. I had to do work on this to move it from point A to point B. And when I do that, I have a gravitational potential difference between this point and this point. I have energy stored as potential energy in that gravitational potential difference. I can do the same thing with charges. I can separate these charges, but to do that, since unlike charges attract each other, I got to do some work to try to get them apart. If I do work on this and I can get them apart like this, and now I have one charge here and one charge here. Now, if I do that with masses, if I separate the two masses and I let this one go, they come back together. I drop it, my potential is becoming kinetic. Exactly the same thing happens here. If I separate these, I'm holding them apart now. If I let them go, if they're close enough, unlike charges attract, they're going to come together. There's something moving here, it has kinetic energy, and these charges are moving. So now those charges that are moving have kinetic energy, and kinetic energy can do work. The point is this. When I take two masses and do work to separate them, I have a gravitational potential difference between the two masses. When I take two charges and I separate them, I have a potential difference between the two charges, but it's not a gravitational potential difference. There's no gravity here. It's not a gravitational potential difference. It's a electrical potential difference. I have an electrical potential difference between this charge and this charge, and the electrical potential difference is just another name for, you got it, voltage. Voltage. Well, hold on a second, Singleton. What are you saying? Are you saying that if I want to make a voltage, all I got to do is take charge and separate it? That's exactly what I'm saying. If I want to have a gravitational potential difference, all I got to do is take two masses and separate it. There's energy stored in these masses. If I want to take charge and separate it, there's energy stored in that charge, and that separation of charge is called an electrical potential difference or voltage. And now I have potential energy stored, not in the gravitational field like this case, but there's an electric field that exists between these two charges that could act to bring these two charges together to do work. Electrical potential difference is another name for voltage. All voltage is, and write this down, write it down, all voltage is a separation of charge. Voltage is a separation of charge. Your battery, your car battery, your cell phone battery, anything that has a voltage, your battery charger, your cell phone charger, what that thing is doing is separating charge to create that electrical potential difference or voltage. All voltage is a separation of charge. A battery separates charge through electrochemical action. That's a chemistry thing. But what it's doing is separating charge. Ooh, let me pause for a second and let that sink in. We spent a long time getting to that, but it explains so much if you think about it. So let me go back to my example. But let me go to the end of what we want. Teaching to the end. What I want is some kind of way to make electric current. Well, by now you know what electric current is. Any kind of current. If I have water just sitting in a pond not moving, I just got static water. If I can make water move, gravity pulls on water and can turn a pond into a stream. Now I talk about water currents. I can take a little boat, put it in the water current, it can do the work of moving that boat downstream. I want to do exactly the same thing to charge. I want to take charge that's static, and I got to make it move. But I can't push it with my finger. The electrons are too tiny. So how do I exert a force on a group of charges that's not moving but are free to move? I do this. I separate charge. When I separate charge, I have an electrical potential difference between the charges, or voltage. Now, since I have charges separated, remember between two masses, there's a gravitational field. Between two magnets, there is a magnetic field. But between two charges, there is an electric field. So even though you can't see it, if God gave you special sunglasses that enables you to see fields, you can look out of yonder and see a gravitational field. You can look between two magnets and see a magnetic field. And with those glasses, you can look between these two charges. And what you will see are lines of force going from the plus charge down to the minus charge. They're invisible, but they're there. You're used to something being invisible in there. You played with magnets before, and you know if you take two North Poles and you put them close together, if you force them on each other, they still push apart. You can feel with another magnet, you can use it to probe around another magnet, a second magnet. You know something's there, it's just invisible. It's exactly the same thing here, same thing with gravity, same thing with magnets. These fields exist, they're invisible, but we can see and feel their effects. So if I have two charges and I separate them, I have an electrical potential difference or voltage. And in that separation of charge, there's an electric field. Now, remember what I said about fields. Fields can do what? Fields can carry force, or fields can carry energy from one place to another. They don't have to touch each other. These two charges never have to touch. So what do you think is going to happen? What's going to happen if I take an electron, one single electron, and I put it in this, if I put it over here, it's just going to sit there because it can't feel any force. But if I take that single electron and I put it right here in this is the electric field. If I take a single electron and I put it in this electric field, then what's going to happen is this electron is going to move this way. I don't care how you think about it. You can use the law of charge to think about it. The law of charge says like charges repel, unlike charges attract. So I have this electron that's free to move. These two charges repel each other. I got a negative and a negative. So this is pushing the electron up. And at the same time that this is pushing this up, unlike charges attract, so this is pulling it up. It has no choice but to go this way. So you can think of it from that point of view. What's really happening is, though, you have this invisible electric field. And once you take that electron that's free to move and put it, as soon as you put it in that field, you're going to feel it want to move up. There's a force of repulsion and a force of attraction acting through the electric field, making this electron want to move up. When I release it, it's going to move up. The key is it's going to move up. So I got something that wasn't moving, I apply a force and it's moving, now work is happening. Once I give an electron kinetic energy, it can do work. It can do the work of lighting up a light bulb. It can do the work of turning your cell phone on. It can do the work of turning the TV. Once I have current moving, I can make things happen, and then that's the world we live in today. Electrons are making things happen. Well, that's a lot. So, definition of voltage. Voltage is a separation of charge. Voltage is a separation of charge. Batteries separate charge. Generators separate charge. If you have one of those lights out that the sun charges them up, the solar cells, they separate. Anything that creates a voltage is separating charge. Let me give you a more mathematical definition. Now what I'm going to do is I show just these separate charges, but we don't deal with separate charges. It's silly to think that. There's no way to take one electron and put it in a field. You can't do that. We deal with groups of electrons, groups of charges. We have a unit called a coulomb. 1 coulomb is 6.25 times 10 to the 18th electrons. And so when we think of charge, moving charge, we think in terms of moving coulombs of charge. Thousands and thousands and trillions of electrons. So I'm going to draw these masses of separated charge. I'm going to draw this. I got some charge here. I got some charge here. And this charge right here is negative. And this charge down here is positive. So I got some coulombs of charge here. I got some coulombs of charge there. And of course, anytime you take charge, and as soon as you separate it between the two, there's going to be an electric field. Just like when I have two masses, as soon as I separate it, there's a gravitational field. I know that because when I hold this out like this, I can feel the earth pulling down on it. You call it weight, but what it really is the earth pulling down on this. The same thing will happen here. As soon as I separate these charges, I'm going to feel them wanting to come together. It's not weight, but it's a force of attraction through that electric field. But here's what I'm going to do. I'm going to make these two masses of charge. I'm going to glue them once they can't come together. I'm going to fix these so they can't come together. So now I have a permanent potential difference between this point and this point. I have a permanent electrical potential difference, or I have a permanent voltage between these 2 points. Voltage is always between 2 points, and now you see why. If I do that, if I fix these two groups of charges, and what you will see between these is the electric field. And we usually abbreviate that E field. And for those of you that know calculus or vector, you deal with vectors, any field is a vector. If you don't know what I'm talking about, don't worry about it. But if you know what a vector is, all fields are vector quantities. So the E field usually is drawn with an arrow over it to indicate it's a vector. You might see that in the book or something. But don't worry about that part of it. Now, if I separate the charges to create an electrical potential difference or voltage, and now I'm going to take some charge, not one electron like I had before, but a group of electrons. So I got a group of electrons right here, but I got 1 coulomb of electrons. 1 coulomb of electrons. I want to take these electrons, this 1 coulomb of electrons, and I want to move it this way. I want to push it up that way. What do I got to do to move this group of electrons up that way? What do I have to do? To move it up, I got to do what? Somebody say it. I want to move these electrons up to here.
You want to subtract an electron or add a proton?
No, I want to know. No. You're not thinking about it the right way. I got negative charge here. I got positive charge here. They're fixed. They can't move. I got 1 coulomb of electrons here, and I want to push it up this way. Now, like charges do what? Like charges repel, unlike charges attract. So, are these electrons going to want to move up that way easily?
No.
The answer is no, because these are going to repel this, and this is going to pull it. It's going to attract it. So, if I want to move it up that way, I have to do what? What do I have to do when I want to move this up?
Work.
Work. Yeah. I gotta do work. So I gotta do work to get this up here like that. I gotta do some work. Well, it turns out that if I do 1 joule of work, moving 1 coulomb of charge, then I have 1 volt of potential difference. If I do, and moving this charge, if I do 1 joule of work, in moving 1 coulomb of charge, then I have 1 volt of potential difference. In other words, what voltage is mathematically, voltage is work per unit charge. Voltage. It's work per unit charge. And so we said that work as units of joules and charge units of coulombs. So a joule coulomb is 1 volt. If you tell me how much work I have to do to move the charge, and you tell me how much the charge is, I can tell you how many volts of potential difference is produced. Now, on somebody's mic is unmuted. I don't know who it is. Check your mics. Thank you. On did I give you guys a supplementary quiz? I think I did. I think there's a supplementary quiz in the week. I don't know. Is there a supplementary quiz in week 2? I think there is. I think there's, but if on the supplementary quiz, there's a question like this. I think the last 2 questions where they give you work done on the charge, and you have to calculate the voltage. Well, there's how you do it right there. If you write this down, and you got 2 questions on your supplementary quiz, and that's 20 points right there. So, that's a lot. Any questions over voltage? It's a pretty easy concept to say voltage is a separation of charge. It's not so easy to talk about all the things I had to talk about for you to really understand how we do that. Questions or comments on voltage? Okay, well, the next thing is current. Voltage is a separation of charge. What is current? I've already told you what current was. Current is charge in motion. Current is charge in motion. How does the charge move? Well, you can see right here that if I have an electron and I put that in the electric field, and I actually have this drawn the wrong way, guys. These arrows should go up the other way, I'm sorry. The electric field goes from positive to negative, so I drew it the wrong way. The electric field actually has direction, it goes this way. So put that in your notes if you're taking notes. I forgot what I just asked. Oh, current. So current. If I take an electron and put it here, that electron is going to move this way. Again, you can use the law of charge to think about it if you want. Like charges repel. So these negative charges, which can't move, are repelling this. They're pushing this away, and this is free to move. And down here, unlike charges attract, so these can't move, but they're pulling this thing. These are pushing it down, and these are pulling it down. This electron has no choice but to move down. So just from the physics of what we've been talking about, you see why current has to flow from negative to positive. The actual path of current is always from negative to positive. Remember that. So what about current? What is current? Well, current is just charge in motion. Current is charge in motion. So if I want to make electric current, I start with static charge, electrons, and I make a move by applying a force, not a contact force, but an action at a distance force. The way I get that action at a distance force is I take charge and I separate it to get an electrical potential difference or voltage, and I take the charge I want to move and put it in that electric field, and if that charge is free to move, it's going to move one way or the other. So current is charge in motion. And to be specific, current is charge per unit time. You want to write this down. Current is charge per unit time. We use the letter I to represent current. Use the letter V or Q to represent charge. We use the letter T to represent time. So I have an equation here for voltage. And I have an equation here for current. It says current is charge per unit time. And remember, charge is measured in coulombs, and time is always measured in seconds. So current has the units of coulombs per second. Current has the units of coulombs per second. If I have voltage, if I have a joule, 1 joule per coulomb, that's equal to 1 volt. Over here, if I have 1 coulomb in a second, that's equal to what we call an amp. 1 amp is a coulomb of charge flowing past a point each second. 2 amps would be 2 coulombs of charge flowing past a point in 1 second. If I have 10 coulombs of charge flowing past a point in a second, I have 10 amps of current. So this is a rate of something. And anytime you have a rate in physics, you always have time in the denominator, some unit, seconds, hours, some unit of time. So, current. Well, that's a lot, guys. We have voltage, separation of charge, current, charge in motion. There's a cause and relationship between the two. It takes a voltage to make a current, and you should be able to explain why. It takes a voltage to get charge moving to make a current. Why? Because I got to have a way of applying the force to that charge I want to move, and we can't apply a contact force, so the only kind of force I can apply is an action at a distance force. So I get that by separating charge to create an electrical potential difference or voltage. And I take the charge I want to move and put it in that electric field, and now that E field exerts forces either up or down on the charge. I can make it move. I can give that charge kinetic energy. And if the charge is moving and has kinetic energy, then I can use that kinetic energy to do work, to turn a motor, turn the light on. Whatever it is electrically you're doing is doing it because those electrons have kinetic energy. That's a lot. I have this sheet here that I have on your blackboard, and I believe we did the first problem already. Now, guys, there's a magnifying glass in the upper left-hand corner of your blackboard. You can zoom in on that document. And we've done this sheet. I think we did problem number 1 and 2 and 3 on here, but I want to do problem number 4. Look at problem number 4, and with the information I just gave you, you should be able to do problem number 4. Go ahead and do it. Take your calculator out if you need a calculator. And see what you come up with. So, of course, we're going to use this equation. Now, guys, when you do work for me on exams, quizzes, homeworks, never give me just the answer. I want the equation first with no numbers in it. You write the equation, you write the equal sign, put the number in it, give me the answer, and then you circle or put a box around the answer. So the correct way, if this was a quiz or something like that, what you would show me is this. I want to see, I call it the working equation. That's going to be that one. So I'm going to write the equation. Current equals Q on T. We have 5 coulombs of charge. So I got 5 coulombs. And the time is 0.5 seconds. So I got 0.5 seconds. And so the final thing, I divide these. I would get 10. My units are coulombs per second. So I got 10 coulombs every second going past that point. But 1 coulomb per second is an amp, so that gives me 10 amps. So what I want to see is this statement right here, and then you would circle your final answer as that or either that. Okay? So, took us a week and a day to get through this. It's been a lot, and we're not even done yet because we still haven't talked about resistance. But I never talk about resistance in theory. I always talk about resistance in lab. because that'll be your first in-person lab you do with me. We'll talk about resistance, what it is, and all of that. So I'm not going to talk about resistance today. Nathan, question.
Will we be coming in for lab tomorrow?
No. Your lab 3 is on Blackboard already. It's something you can do from home. It deals with charge. We will come in next week, though. My plan is our first face-to-face lab will be 1 week from tomorrow. So, guys, if you have not purchased your digital multimeter, hopefully you've used this lag time that we've had to get your multimeter. But if you did not purchase it, you want to make sure you purchase it before next Tuesday. Of course, if you didn't purchase it, you couldn't do lab 1 because you had to watch the video and you had to make a picture of your meters. So I know you all have them, but if you don't, you want to make sure you show up here 1 week for tomorrow with your digital multimeter. And I will have more to say about that lab before we meet face to face. But as long as I'm happy with the COVID numbers. My mom got her vaccination. And so I think we're good to meet face to face. Just make sure you bring a mask with you, but I'll say more about that later. Anybody have any questions on this stuff? I got one more thing I want to show you before we run out of time. Any concept wasn't clear? Anything I need to repeat? Do you see what's going on? Any questions at all? And sometimes you might have to watch this stuff twice, the video, to really get a handle on what's going on here. Any questions or comments? If you have the topic sheet at the bottom of it, there's one more section that on resistance. I'm not going to cover that today. But there's also the electric circuit. I want to finish today's conversation talking about the circuit. So let me show you something real quick, and then I'll stick around after class in case somebody has any questions. So here's what we know so far. We know there's voltage. And all voltage is a separation of charge. Anything that produces a voltage, what that thing is doing is separating charge. I know there's current. Current is charge is moving. It takes a voltage to make charge move. And I'm not going to go through the details of that, but you now know the electric field, action at a distance forces. If somebody paid you enough money and gave you enough time, you should be able to go through that and explain how this causes that. And anytime something moves, there's always opposition to that motion. And in the case of mechanical objects like a ball rolling down the hallway or anything that's moving and is not propelled by some engine or something is eventually going to stop. Stop because friction acts on it. Friction is opposition to motion. Well, electrical friction is opposition to current flow, and that's resistance. Now, don't be satisfied with that because I got a lot more to say about resistance. I'm just going to do it in the next lab. I'm not going to do it in here. I'm going to need like an hour for that. Resistance is a lot to talk about. But there's the big three: voltage, current, resistance. So you got to know the names. You got to know what they are physically: separation of charge, charge in motion, opposition to current flow. You got to know the units we use to represent them. We use a capital V to represent volts. You might have a battery that's 12 volts, like your car battery. You have current. We use coulombs per second. What a coulomb per second is an ampere. So you might have a circuit breaker in your basement that's 15 amps. And resistance, they usually use this uppercase omega, but sometimes they write out the word ohms. Either way, I don't care how you do it. So they're the units. But what I want to end the class talking about is, in electrical engineering, we have these special symbols we use to represent these concepts. And so I want to give you those symbols. And then once we have those symbols, we can put those symbols together into something called a circuit. And then I have what's termed as a schematic diagram. So I want to give you these symbols. So for voltage, if I want to represent graphically a voltage, there's three ways to do it. I can show it like this. I can show it like this. Or I can show it like this. So notice a couple things. Notice on these symbols, I have plus and minus sign. That's something called polarity. When you have voltage, you got to show polarity. And you'll in your lab, you'll discover hopefully what that means, the term polarity. So I got to show the plus and minus sign. So by definition, the long side of the symbol, these two, is the positive polarity, and the short side is the negative polarity. Now, this right here is called a battery. This is a battery. And this is a cell. So I'm not going to go into the difference between them today. I think that's when we get to week 3, we talk about the difference between a battery and cell. There is a difference, and I want you, since this is your major, I want you to know the difference. But in here, we can use either one. They're really different, but you can use either one in here, I don't care. So long as when you leave here and go outside that door, you know the difference between the battery and the cell. And this one is just kind of generic right here. You can use that. So if I want to represent a voltage of 12 volts, I can draw this and then put 12V by it, or I can show the same 12V by any of the other symbols. So those are the graphic symbols we're going to use to represent voltage. To represent current, we are going to use an arrow. An arrow. And then to represent resistance, we're going to use a symbol. It looks like the bottom of a saw, like you saw wood with. It looks like this. So now, instead of talking about voltage, current, and resistance, I can just show these symbols and you know what I'm talking about. So for example, I might have a voltage source. I'm going to draw a voltage source. I'm using this symbol, but I can use any of the 3. I might have a resistance. And maybe my voltage source is, I don't know, maybe it's a 10-volt voltage source. So I'll do like that. Those will show my polarity. And maybe my resistance is 2 ohms. So I can show that. Well, what you can do once you got these symbols down, you can actually draw wires to connect the voltage source to the resistor. I can do this. And this is called an electric circuit. A circuit is a closed path through which current can flow. So if I wanted to show the current, now watch what I do. Watch what I do. If I want to show the current, I just put an arrow here. Put my current arrow like that. Now, you might think to yourself, well, hold on a second, Singleton. You did that wrong. You told me that since when we create an electrical potential difference, if this is positive charge and this is negative charge, and the electric field is like this, I know from the physics of what you just showed us that if I put the electron here that's going to make the current, it's going to flow in this direction. So current is actually flowing this way. And that would be correct. Physical current flow is always from negative to positive. Now, I don't know if you have your book handy, but whenever you get your book, or maybe use the link that I sent you, if you look at the very front cover of your book, it says Electronic Fundamentals, but in the very bottom of the title, it says Conventional Current Flow. Conventional current flow. There's 2 kinds of currents. There's actual current, which is the red. That's called electron flow. That's the path the current really takes. But then there's another kind of made-up current where we assume current flows from positive to negative. That's called conventional current flow. So big boys use conventional current flow. I don't have enough time. I only got like 2 minutes. But next video or next lecture, if I think about it or you ask me, I'll tell you why we have conventional current flow. Doesn't really matter. If you like the actual path electrons take, you can make all your current arrows go this way. But I'm going to do conventional current flow. And I'll tell you why later on. So here we go. We're finished with chapter 2. Week 3 stuff is already posted. Actually, week 3 is 2 chapters, chapter 3 and 4 together. So you got a lot of reading to do. So don't get behind on your reading. You have the lab to do. That lab is due tomorrow at midnight. So make sure you look at lab 3. The homework and all that, I'm not collecting that till next Tuesday, so you have time, if you got behind on that, to get caught up. So, guys, all the physics stuff is over. So from here on out, it's all electronic stuff. This is where chapter 3 is where the study of electricity actually begins. Anybody have any questions or comments for me before I sign off?
I have a question on homework 1.
Sure.
On number 30, it says the number of microamperes in 1 milliamperes.
Wait a minute. Tell me what it says.
The number of microamperes in 1 milliamperes.
Okay, so we have 1 milliamp. We have 1 milliamp, right? Is that what you said?
Yeah, microamperes in 1 milliamperes. Yeah.
Okay. So they gave us 1 milliamp, and what they really, here's what they want. Here's they ask it a funny way, but what they really want to know is if I have 1 milliamps of current, how many microamps is that? That's what they want to know. So all they're saying is if you have this, if you have 1 times 10 to the milliest, 10 to the minus third, if I had that many amps, how would I change that to microamps? How would I write that power of 10 as 10 to the minus 6? And the way you think about that is, well, how'd you get this 10 to the minus third? You started over here and you moved that decimal place 1, 2, 3 places, and you're able to write it as 1 times 10 to the minus third. So you got to move it another 3 places if you want to write it as a minus 6. So this started off like this. And you said, all right, well, that's easy. This is just 1, 2, 3. So that's 1 times 10 to the minus third amps. But if I want to write that as a 6, I got to keep going. I gotta add 3 more zeros. So I got to keep going. I got to go 1, 2. I got to add some zeros here. I go 1, 2, 3, 4, 5, 6. So I'm going to have 1,000 times 10 to the minus 6 amps, or I'm going to have 1,000 microamps. So the best way to think about it is write this as a power of 10, write what they want as a power of 10, and then ask yourself, how would I go from a minus 3 to a minus 6? Well, you already moved it over 3 places to get to the minus 3. Just move it over 3 more to make it a 6. Does that make sense?
Yeah. Thank you.
Great. Thank you. Okay. Well, guys, anybody else?
Yes, sir. It's Riley. So, if I want to upload my homework, so I want to scan it or to do it through the computer. So,
I'm gonna. I don't think I made that uploadable. The homework. I'm gonna have you bring it in on Tuesday. But
okay.
you got to upload your lab though.
Okay.
Now, the lab, I saved the lab document as a Word document, so you don't really have to print that out. You can actually type on there. I don't think there's any drawings or anything you got to make. So you can actually type the answer, so you never really have to scan that. But if you ever have to write something by hand, you would have to scan it.
Oh, okay.
But I
Thank
think
you.
you're okay. Yeah, I think you're okay for the next couple of assignments. Okay. All right, well, guys, I'm going to sign off now. You have a great rest of the day. I will see you guys, I guess I'll see you on Wednesday, and we'll start chapter 3 and chapter 4.
See you Wednesday.
Thank you.